This is a great pleasure that you are here, and yes, it's a great pleasure that you are here, and people came after these announcements. Okay, so we will try to do more activities like that. So if you can tell your colleagues and your friends to come here and on Zoom or on in real person, we will do more activities, and we hope that we will have more and more people, and will be something. It's interesting. So today we have the visitor from Paris, Riccardo Brasca from University Paris-Cite. He's here 2 weeks, 3 weeks visiting us and working and doing mathematics. But also he will do this mini course to teach you some stuff between computers and mathematics. Okay, so maybe let's start, and it's a great pleasure to have him today. Okay.
Muchas gracias, Daniel. So thank you very much for coming. I'm sorry, but I'm not able to speak in Spanish, so I will speak in English. So as the title of my mini course suggests, I'm gonna explain what formalization of mathematics is. So let me start with a very brief introduction about this subject. So formalization is the process of using a computer to reason. So using a computer to do mathematics is something that is not new at all. For example, you may already have used some tool like Sage or Maple or Mathematica, or I don't know, MATLAB or stuff like that. So you can use computer to do big calculations or big simulations and stuff like that. This is not at all what I'm gonna talk, because you see, when you use, for example, Maple to do a big computation, Maple is able to do the computation, but it doesn't know the proof. I mean, the mathematical proof he's using. Someone that knows them has written the code, and Maple use the mathematical results, but doesn't know the proof. So what you're going to do is rather different. Is really using the computer to study proofs. So the software used to do formalization are called the proof assistants. Okay, this is just the name of a piece of. They are just piece of software. There are several of them. For example, some of them are really quite old. For example, there is Isabel, that is one of the oldest, I guess. Is from the 70s or 80s, I don't know. In any case, we will use Lean, that is a fairly recent software. But I mean, I'm gonna show you Lean in practice. So what you're gonna do is to use Lean, but essentially everything we are gonna do with Lean can be done also with the other proof assistants. And I'm gonna use Lean for the very good reason that is the one I know. Okay, so let me introduce you to Lean a little bit. So Lean is a piece of software that has been developed by Leonardo de Moura at Microsoft Research.
So Riccardo,
yes.
One question. So maybe I want to remark that if someone want to ask you something, don't feel shy.
Yes. If you have, of course, if you have questions, just don't be shy. Just ask questions. I mean, I'm here for that. So
on Zoom too, if you want, we are following the computer, so if you have questions
to look at questions, so
if you can ask, or you can write, and I will transmit.
Okay, thank you. So it has been developed in 2013. So what is Lean in practice? It's a programming language. So it's a functional programming language, if you know what it means. But I mean, if you don't know what functional programming language means, just forget about it. That is powerful enough to express mathematics. And we will see that it's indeed possible to write mathematics in this programming language. It's an open source project. So this is something that is pretty important for me. So in practice, it's free to use. So this is already very good. But since we are going to use this software is also used to check mathematics. It's important that maybe it's important that we can check that the software is well written. And since the software is open source, everybody can read his code source and everybody can check that it works. So, I mean, now the current version is the 3.48. I mean, this is not so important, but very soon there will be Lean 4. That it will hopefully be quite a revolution. So it will be really better than Lean 3, but we will see. We are going to use Lean 3 in any case. So Lean comes with a mathematical library with a lot of theorems already proved in the library. So this is, think about, so the name of the library is MATLib, and think as MATLib as an advanced undergraduate student, or maybe a beginner graduate student in mathematics. So it has around 1 million lines of code, and we are going to use it a little bit, but we are not going to use the full library for the good reason that, I mean, all the examples I'm going to show you are already done in the library, essentially. So if we use the full library, I mean, the proof of anything is just something like it is already in the library. So someone else is proving it. But we are, I mean, I'm going to try to show you how the proofs are done. So we will use some part of MATLib, but not the whole one, not the whole MATLib. Okay, let me explain a little bit more details how a proof assistant works. So it has two components. The most important one is the kernel of the proof assistant. That is the component that checks that the proof is formally correct. So the kernel takes mathematical proofs, and it really checks that there are no mistakes in this proof. So checking correctness of the proof from the axioms. So you don't have to know what the axiom of mathematics are. Don't worry about that. But the kernel knows the axiom of mathematics and is able to check the proof using only the axioms. Then there is another part that is called the elaborator. So what the elaborator does, in practice, it takes something that a human being writes, so something like a mathematician usually write on the blackboard, and it translates to something that the kernel can check. Because the kernel is something that is very stupid, because he only has to check that the proof is formally correct using the axioms. So the proof must be extremely precise, and a human being cannot write such a proof. It's completely impossible to write a completely precise proof. So the elaborator translates the human written proof to something the kernel can check, and then the kernel says, okay, the proof is correct or there is a mistake.
Riccardo?
Yeah.
Someone asked if there is a possibility to prove by absurd
in Lean?
In Lean, yeah.
Yeah, sure. Yes. Lean is completely classical. I mean, MATLib is completely classical, if you know what it means. So we have proof by contradiction, we have the axiom of choice, the goal of Lean, especially MATLib, is to do mathematics as mathematicians do mathematics. So we don't care too much about reasoning about constructive mathematics and stuff like that. So the axiom of choice, the exclude the middle, they are all there. We will see a proof by contradiction, I think. So normally a user only interacts with the elaborator. So in practice, we will see examples of that, but in practice, we will write proofs, and the elaborator will take our proof, will translate in something that we will not see, but we will see that the kernel will be happy or maybe not. If we are smart enough, the kernel will be happy, but we will see. In any case, normally we only interact with the elaborator. So the part of the proof assistant that translates proofs. Okay, so before starting playing with Lean, maybe you are asking, okay, but why should we be interested in this? So why formalize mathematics? So one simple explanation is that we are checking correctness at a superhuman level. Really, if the proof assistant say the proof is correct, is extremely unlikely that there is a mistake. Of course, I mean, the proof assistant has been written by humans, so in principle, it's possible that there are bugs inside the proof assistant, but the kernel is a very, very small piece of software. So it's extremely unlikely that there are bugs in the kernel. And also, people have written independently several versions of the kernel, and they all agree. So I would say that it's really essentially impossible that there is a mistake in the kernel. So if the proof assistant says the proof is correct, it's unreasonable to doubt about correctness of the proof. Then formalization is a challenging process. I mean, it became really interesting after some time. Unfortunately, in my mini course in 3 hours or whatever, it's not really possible to grasp all the interesting part, but at some point it really became challenging and it really became interesting. For example, at some point it can help and better understanding normal mathematics. So you take a real mathematical statement, and if you want to formalize it, I mean, in the process of formalizing it, at some point you start understanding it better. So it can really help. It can really help in doing mathematics. If you are interested in this, I mean, I will give a talk more for mathematicians, I mean, for professional mathematicians in 2 weeks, where I will give more detailed example of this phenomenon. Something much more practical that we can have if we start formalizing a lot of mathematics, at some point we will have a database of statement. And so we can maybe start using artificial intelligence or whatever, I'm not at all an expert, to hope that the computer will be able to start doing proof automatically. So now this is science fiction. Today, the computer is able to do really stupid proof by itself. So this is already possible that the computer does a proof automatically, but these are proof of really stupid things. But who knows what will happen in maybe 10 years or whatever. So what we are doing is also building this database, and maybe this database can be used by in 10 years or maybe less, I don't know, to start automatizing the process of writing a proof. So just to give you an example of a project I've been involved in the last 2 years. So with around a team of 15 people, led by Johan Kommelin, we formalized a very recent theorem of Dustin Clausen and Peter Schulze. Peter Schulze is a Fields medalist, so he has a Nobel Prize in mathematics, essentially. And he proved this very, very difficult theorem, and we formalized it. So it took us 2 years, and you see this picture is any circle. Maybe it's not very visible, but there are a lot of small circles. So every circle is a theorem we had to formalize, or it was already in the library. But in any case, he had to be formalized to get the final results. That is this red star here. And there are more than 25,000 of them. So to formalize these very recent results, or very difficult results in mathematics, we had to use or formalize more than 25,000 results. And at the end, even the authors say that thanks to our work, creepy, okay? Thanks to our work, they understand better their own results. So they said us that, because we discussed with them a lot, and they said that discussing with us and solving our problems in the process of formalization helped them to better understand their results.
So one question about the picture, for example, I don't know, the position of it's a random choice? Or?
Yeah, I mean, I use this. So, I mean, this is you cannot see, but it is. No, maybe it doesn't like this. No, I don't know. Okay. So this is a graph. So two points are connected. So each point is a theorem, and 2 points are connected if one theorem uses the other one. So you cannot see really the edge, but you see that here there are a lot of edges. Maybe you can see this one. And the position is pretty random. It's just, I mean, I used a piece of software called Gephi to make the picture that try to put all the dots in a position such that everything is visible. But so this doesn't mean anything special. I mean, the position is really random. It's just to make a nice picture. And the colors corresponds more or less to results in various subject of areas of mathematics. For example, we have analysis, algebra, discrete mathematics, topology, blah, blah, blah.
But one theorem in the middle of the two colors, that means it's very related using stuff from both areas.
No,
No?
I don't know. I don't know. But if you want to know funny things, I mean, the final results that you can guess, it's in the orange region is actually blue.
Oh.
Yeah. I mean, this
Okay.
is the software that decided that. But so yeah, okay. So this is just to show you that it's possible to do something really, really interesting today using, using this proof assistant. So let's now play a little bit with Lean. So let's enter really in the heart of the subject. So what I'm going to do today and tomorrow essentially is showing you Lean. So I'm going to show you some small proof just to explain the basics. But the best thing you can do if you really want to understand how this works is to try to prove stuff by yourself. I mean, as usual in doing mathematics, it's interesting to listen to someone else, but at some point you have to do exercises to become good in doing mathematics. So for Lean, what you can do is just to search for a Lean theorem prover in Google or whatever. You should end up into this website. Sorry, my phone. Okay, that is. So this is the official website of the Lean community. So if you want to install Lean on your computer, you have to go here where there is get started, and there are instructions for installing if you use Linux, Mac OS X or Windows. I mean, I only use Linux, so I have no idea how it works in other systems, but it shouldn't be too hard to install it. So I think that these slides are available somewhere, no, Daniel? So you can just click. I mean,
that is in the web page of the.
Okay. So you can just
of the mini
download
course.
my slide and click on the link.
Look at the web page of the mini course, and you will find some class season 1 notes. There you click and you find this.
By the way, if you look for Lean theorem prover in Google, you find it very quickly. So if you don't want to install it, it's possible to play with Lean anyway, using Gitpod. So Gitpod is essentially a free service that hosts a full installation of a lot of programming languages, also Lean. So you can also use it. It's a little bit slower, but it works. But the only thing is that you need to have a Gitpod account. I think you can use a GitHub account if you have it. But if you go to gitpod.io, then at some point it asks you to log in, and you can create an account. It's completely free, so you only have to give them your email address and so on. So I really encourage you to install Lean on your computer if you want to try, or at least to create an account on Gitpod to try to play with it a little bit. I mean, it's interesting to see me doing stuff, but I'm really sure that the only way to learn is to try to write some stuff.
But maybe it's a good moment to say that next week.
Yeah, next week, this is what we are going to do in the computer room. Which number?
2008.
So in that room there are computers available, but try at least to have a Gitpod account to use the computer there. So if you go to this web page, you see that there is this line learning resources, where there are really a lot of tutorials or stuff like that to learn Lean. What you're going to use is this mathematics in Lean. I really encourage you to also have a look at the others if you want, but we will focus on this new resource, mathematics in Lean, so that it can be read online like this. So you see that, I mean, there is a lot of explanation, some proofs and blah, 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 but it can also be used directly with the computer. I will maybe show you tomorrow how to do it with Gitpod, for example. But so what I'm going to do is just to explain you a shorter version of what is in this tutorial. But if you really want to go a little bit further, I really suggest you to read all, to read this tutorial and try to do as much as as much exercise as possible. Oh, sorry. Okay. So I think this is the end of my introduction. So really, don't forget to go to download the slides and to click on these links if you want to try. So now I'm gonna really show you Lean in practice and to start doing some small proof. Okay, so this is Lean. So I'm using it in an editor that it's called VS Code. There are several editors if you prefer using Emacs or VI or whatever. I suggest you VS Code if you are a beginner in programming, but I mean, it's a very famous editor. You can use it to program in Python, in C++, or whatever you want. There is a Lean extension that is, I really suggest you to install in such a way that it really interacts well with Lean. So is the font big enough for everybody? I can maybe, well, okay, we will see.
Bien o no,
okay, okay. We will see if it's possible to use it like that. So the first, just ignore the first the lines import blah blah blah. This is just to start using a little bit the library, but just forget about that. So the first important thing to understand in Lean, you see that now here there are some mathematical expressions somehow. Sorry. So the first important thing to understand, and this is maybe the only tricky part, is that in Lean, any expression, so I mean anything, has a type. So this is a concept that doesn't exist in standard mathematics. So it can be a little bit, it can look a little bit strange at the beginning, but it's really nothing difficult. So you can anything you write as a type. Well, essentially, think as a type as its home, the home of the thing you write. So you can check the type of something using the command check. So here I write check 2 + 2, and you see that Lean here responds and say 2 + 2 is a natural number. Okay, so it doesn't care that 2 + 2 is equal to 4. We are just asking what is the type of the expression after check, and Lean says the type of this expression is n, is a natural number. Okay, so anything, so mathematics, you would say that 2 + 2 is an element of natural numbers. Here you say that 2 + 2 has type natural numbers. Yes? No? Okay. So
the natural numbers have type what?
Okay, so don't listen to this difficult question. They have type. Now there is the Russell paradox, blah blah blah. So there is this is going to be technical, but
okay.
It's I don't want to speak about this, but because you enter immediately in some Russell stuff, paradox, and of course everything is done, but ignore this question.
Perfect.
Okay. Okay, so okay. N is a type. If you want to know how can you, for example, type literally this fancy letter, you can just go with your mouse over the letter, and you see that VS Code helps you a little bit and say type N using /n. Okay. So now let's see another example of type. So let's first of all give a definition. So we define, so def, it means we are going to give a definition. We define f that take a natural number x, and it returns x + 3. Okay, so what is f? F is just a function from natural numbers to natural numbers. Okay, which function? The function that sends x to x + 3. Okay, and in it, if we ask Lean to say what is the type of f, say nothing special. It says, you see, f has type n to n. So now here, so you see that, okay, maybe I'm going to increase the font again, but you see that it says this is really the standard terminology. I mean, the standard symbols we use in mathematics. So F is as type n to n. And you see that if you are used to the use of colons in mathematics, this is really the standard notation. So when I say that 2 plus 2 as type n, writing 2 plus 2 colons n, this is not so standard in mathematics, but for F is perfectly standard. This is, I mean, a mathematician would write exactly this. Yeah, this is a nice side effect of type theory. But okay, so if you are interested in this kind of foundational question, the point is that the axiomatic system of Lin is not set theory, but it is type theory. But it's not at all important to understand this type theory. Yes.
What would you have to type to make this a function from n to r?
So I have to import something about real numbers because otherwise.
Okay, sorry.
Data.real.basic, I guess. Yes. Oh.
Okay, you have to force.
So now, yeah, exactly. Now what I say is take x a natural number, take x plus 3. That, I mean, for Lin, x plus 3 is of course is of course another natural number. And I say to Lin, yes, but it's natural number, but I want to consider it as a real number. Lin knows how to do it. So it's not asking, how can I consider a natural number as a real number? He knows how to do it. Man, that's Lin magic. And you say that now F is a function from n to r. Okay, there is there is one special type I absolutely need to talk about. This is the type of proposition. So it is the type of mathematical statement. So you remember that anything you write has its own type. So 2 plus 2 equal 4 must have its own type. And what can be the type of 2 plus 2 equal 4? It's not natural numbers. This is 2 plus 2 equal 4 is not natural number. 2 plus 2 is natural number. 4 is natural number, but this is a statement. This is a mathematical statement. And if we ask Lin, what is the type of 2 plus 2 equal 4, sorry, it says is a proposition. So this is some sort of special type that has a special mathematical meaning that is the type of mathematical statement. And be aware that this has nothing to do with the fact that 2 plus 2 is equal to 4. The fact that this proposition is true. If I ask to check 2 plus 2 equal to 5, it will still say it is a proposition. They have the same type. Of course, there is a big difference. This one is false. The previous one was true. But both are proposition. Both are statements. One is true, one is false. But both are proposition. Okay? What happens if I try to write something that doesn't make any sense? For example, now I want to say, remember that now f is our function from n to r. Now I want to know if 2 plus 2 is equal to f. You see, this is not a mathematical statement. This doesn't make any sense. No, because you cannot compare something that has type natural number with something that has type something else. Indeed, if I write check 2 plus 2 equal f, I'm really surprised that it's not complaining. Really?
2 is a constant function.
Yeah, I must have done something like that. Oh, okay. Yes. Sorry, there is. Let's really force him to consider. Oh, okay. Now, yes. Thank you. So, okay. Now I say, is it true that the natural number 2 plus 2 is equal to f? And you see that it's not saying the type. It's saying type mismatch, blah blah blah. Is raising an error. It's saying what you wrote doesn't make any sense. So if you are curious of what was happening before, Lin is trying to help us. So he knows that this thing doesn't make any sense, but he found a way to transform the thing on the left to a function. And as he said, it's surely the constant function.
So you can just compare types with the same type. something with the same type.
Exactly. Don't
No,
enter,
sorry.
don't enter about this.
Yeah.
Yes, you can only compare things that have the same type.
I see.
That doesn't make any sense to compare things that don't have the same type. But I know if you are thinking, yes, but now this is stupid because I want to say that 1 is smaller than pi. The natural number 1 is smaller than the real number pi. Technically, this is not possible because they don't have the same type, but Lean will be smart enough to understand, now I have to put natural number in the real numbers. So this will happen under the hood. As here, you see, here was even too smart for me, but so I was a little bit surprised, but if what you write is not precise enough, so this is the elaborator doing stuff. The kernel would never accept this, but the elaborator is saying, yes, you have to put this, you have to transform this number into the constant function, blah, blah, blah. Okay. So here is another example of a proposition. So this is a pretty well-known theorem. So it's Fermat's theorem that maybe you have already heard about it. So we take 4 natural numbers, x, y, z, n. So you see that this is pretty, the proposition is pretty readable for all x, y, z, n natural numbers, n bigger than 2 and x times y times z different from 0 implies that x to the power of n plus y to the power of n is different from z to the power of n. So this is a proposition that is what it's usually called. I mean, there are 1 million equivalent formulations, but this is what is usually called the Fermat's theorem. Yes.
How does the interpreter know how to put the parentheses? Because I can read it in several ways.
So the parentheses, I guess that this one has the highest priority. So the parenthesis is something like that. I mean, so if computer science don't like using parentheses, so this is completely, yes. So you see now it's even less readable than before, but so this thing implies that x to the n plus y to the n is different from z to the n. Okay. So probably, yeah, I don't know, but I mean it's the statement of Fermat's theorem. So, and if we ask him, okay, what is the type of Fermat's theorem? Of course, it is a proposition. Okay. Now you can see your first Lean proof. So now we didn't prove that 2 plus 2 is equal to 4. We just state that 2 plus 2 is equal to 4. Let's prove it. So so now we say theorem. We give a name to the theorem. We call it easy, and we write colon 2 plus 2 is equal to 4. Now we have colon equals and the proof. So ignore the proof for the moment. This is a very easy proof. But so you see that Lean is not raising any error. So the kernel is accepting this as a proof of 2 plus 2 is equal to 4. I know that this proof looks unreadable because it's just RFL, but I will explain what this means in a minute, I mean in 5 minutes. So now we have proved a theorem. Okay? So there is one last tricky question about types. What is the type of easy? You see, it's easy. It's not a proposition. The proposition is 2 plus 2 is equal to 4. Easy is we proved this theorem. So if you see, if you check the proof of, if you check the type of easy, it says that the type of easy is 2 plus 2 is equal to 4. This is yes, I know. This is the only tricky part. 2 plus 2 is a proposition. So the type of 2 plus 2 is proposition. Now there are essentially 2 possibilities for a proposition. A proposition is either true or false. If a proposition is false, there are no elements of type the proposition. If the proposition is true, a proof is an element of that has as type the proposition itself. Yeah, I know this is very strange from a mathematical point of view, but you can forget about this in 5 seconds. But it's probably, I think it's interesting to show you at the beginning. So you have to think that easy is a proof of the fact that 2 plus 2 is equal to 4. Ignore how Lin constructed it. It constructed it using this keyword, but the idea is that easy is a proof of a proposition. Which one? 2 plus 2 is equal to 4. So any proposition that has something of his type is a true proposition. Okay, and if a proposition is false, for example, it's impossible to construct something of type 2 plus 2 is equal to 5, because this is false. I mean, morally, this is a false proposition, so we cannot build something of type 2 plus 2 is equal to 5. But we can build something of type 2 plus 2 is equal to 4, because we can provide the proof of this fact. And this is, in practice, has the nice effect that if you write stuff, if you write implications, so if you have a proof of P and you know that P implies Q, you see, if you write implication as just one arrow, if you have an element of type P, you apply the arrow, if you have an element of type Q. So if you know that P is true, you have something of type P, you know that P implies Q, but you know that Q is true because you have something of type Q. I mean, we will see examples of this, but this is just some type theory magic that is not necessary to understand. I think it can be nice. Okay, so let's now prove Fermat's theorem. So you see that now we want to prove Fermat's theorem, and Lin is not raising an error. So the proof is very easy. It's just this keyword, sorry, that it just means, come on, Lin, accept that is true. And you see that, so there is no error, but there is a warning. There are these yellow squiggle lines saying that I know that you don't really prove it, but now you can use it. If I ask Lin what is the type of hard, it says it's a proof of Fermat's theorem. But of course, I mean, if you start using this, everything there will be warning everywhere saying yes, you can use it, but you are cheating. Okay, so just to show you.
But sorry, didn't Lin just accept that it's correct? Your proof SORRY.
No, what? Sorry.
So the proof is called SORRY.
Sorry, yeah. Sorry, it is a keyword saying accept it as an axiom essentially.
Ah, okay.
It's a way of cheating. You see that this theorem easy. There are no squiggle lines. Here there is this yellow thing, and you see, declaration uses sorry. So I know you are cheating somewhere. So this is useful if you have big proof, and you say, okay, I will prove this later, but now I want to use this as we do in normal mathematics. Something lemma 2.61, we will prove it later, but let's use it to get the main result. So okay. Now I just want to show you a proof produced by the elaborator. So
Riccardo,
yes,
there is a question from people there, and it's difficult. Which is the logical system of types?
Is type theory. So the axiomatic system of Lin is type theory. I'm not an expert in type theory. You can Google what type theory is about. What I can say is that the axiomatic system of Lin is equivalent to ZFC, so Zermelo-Frankel with the axiom of choice, plus a countable family of universes, a countable families of inaccessible cardinals. So it's yeah, it's a different system from Zermelo-Frankel axiomatic set theory, but it is provable that is equivalent. I mean, adding some large cardinals, but so, and let me stress, there is absolutely no need in understanding all this stuff to use Lin. If someone is curious about the axiomatic Lin is using, you can dig up and get to the axioms. But when we do normal mathematics, we totally ignore the axioms. Here is the same. if you are interested, you can study it, but it's not necessary. So let's see a more interesting proof. And this is unreadable by, I know it's unreadable and is made on purpose. So let's prove this example that for all m and n natural numbers, if n is even, then m times n is even. So you see, this proof is something that is almost checkable by the kernel. And we don't want to write proofs like that, because this is difficult to read. There is this strange lambda symbol, then there are strange brackets. It's unreadable. It's completely unreadable. So this is not the way of the kind of proof we are going to writing, because they are essentially unreadable. What we are going to do is to use more the elaborator to help us writing more understandable proof. For example, here is the same proof, but written in a much more clear way. So this is what really we are going to do. So we take the same example. So for all m and n in NAT, I don't know why it's written NAT and not. Okay, now this is nice. So for all m and n natural numbers, even n implies even m times n. Okay, so this is essentially it means that if you have an even number, you multiply by any other number, the result is even. Okay, so let's have a look of what really Lean does. So the syntax is the following. We have this example keyword. The example is like is like the theorem keyword. It's just that we don't provide any name, but this is exactly the same. Then there is the colon, the statement, then colon equals, and now we have to write the proof. So we write the proof between begin and end. So if you have already used LaTeX, for example, think as begin end as begin proof end proof. So we write begin end, and now we have to write the proof. And you see that what we are going to do is to use this part of the screen on the right that I didn't mention until now. So this is Lean brains. So we can see what Lean is thinking. Now it's thinking something very easy, that we have one goal that is proving what we're going to prove. I mean, what we have to prove. So it didn't do any. It didn't do anything special. It's just saying your goal is to prove the statement you have to prove.
So you say that is the brain of Lean.
Yes.
That is the before you mentioned two stuff, kernel and there is no relation with that.
No, no. Here, this is just something that is helping us to interact with the proof assistant. But so what the elaborator will take what we write between begin and end, and it will produce something like that. And it will send this thing. So you see that this is much more. I mean, I will explain what all of this means, but you see that this is more readable than this. So the elaborator will take this proof written by us, will translate in something unreadable that you don't want to see at all, and the kernel will say I'm happy or no or not. We will see what we say at the end of the proof. But so now Lean is saying you have to prove that for all m and n natural numbers, blah 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 blah. So this is okay. It's exactly the statement we have to prove. So how do we start such a proof? Well, I would say let m be a natural number. So I would say introducing a variable m. So I can say intro m. So you see that now Lean's brain changed. Now he says, now you have a natural number m, and you have to prove that for all natural numbers n, if n is even, then m times n is even. And there is no reason to call it m. I can call it, I don't know, t if I want. But let just be consistent and keep on using the same letters. So now the statement is another universal quantifier. So how do we start this proof? Saying, okay, now we took m, let's take also n. So I can say intro m n, just adding an s here. And now Lynn says, now what you have to prove is that if n is even, then m dot m times n is even. So we also introduce an hypothesis. That is what is written here. So intros m and h, and you say that m and n are natural numbers, and h is the assumption that n is even. Okay. So now what we have to prove that m times n is even. Okay, this is something very, very easy. So maybe you forgot what even means. This is something very nice that Lynn can help us in. If I just click on even, you see that it shows me that even is a proposition, and I can even go, if I click go to the definition. Oh my God. Okay. Okay, sorry. I can check the definition of even, okay, that for some stupid reason is not exactly what you think, but essentially being even means that there exists k such that n is equal to 2 times k. So now we have to think about the proof. Why this theorem is true? It's true because if m is equal to 2 times k, no, sorry, if n is equal to 2 times k, then m times n is equal to 2 times m times k, I guess. So what can I do? I know that h means that n is even, so I can obtain the number whose n is the double of it. So I can just say obtain khk. I will explain more in more detail this obtain keyword in 5 minutes. But you see that now here I had h saying that n is even, and now I got another natural number k, and the fact that n is equal to k plus k. Now I have to prove that m times n is even, because why it's even? Because it is the double of m times k. So I say to Lynn, okay, use m times k. And now he asked me to prove that it's true, that m times n is equal to m times k plus m times k. And why this is true? But now this is very easy because we know that n is equal to k plus k. So I can just say rewrite n. So rewrite n will replace n by k plus k everywhere here. So you see that when I click here, n has became k plus k. So you see. And now why these two things are equal? Because we have the distributivity property. So all this stuff are already in the library, and we will use it. We will see that at the beginning is slightly annoying I mean, it's slightly difficult to get used to all these small lemma already in the library, but at some point it became natural. So I say rewrite mul add. Mul add it says that when you multiply by an addition, it's the addition of it's the distributivity law. And you see that if you apply distributivity law to this thing, now the left-hand sides became exactly equal to the right-hand side. And so Lynn knows that this is true. And you see that the kernel says, I'm happy. And we see goal accomplished. So I know that this is still not so easy to follow. Even if it's a very simple proof, there is this strange keyword intros, obtain, use, and rewrite. We see these several times. At some point, you will get used to them.
Just to confirm, sure. All the green stuff are comments.
Yes, the green stuff are comments. I can erase them. And
the goal would be that in some future you only write the green stuff.
I mean, we are not that far. This proof is this is I can really prove this I can almost automatize this proof. I don't want to show you now because otherwise you can automatize all the proof I'm going to show you because there are proofs of very simple statement. We have some automation. It's not very interesting, meaning that you cannot ask to prove that there are infinitely many prime numbers. Because the computer is not able to do it by itself today, but maybe we'll be able to do it in 5 years, I don't know. But this is completely stupid. There is nothing to do in this proof essentially. So this is really, it can be automatized, but I don't want to show you because otherwise you can just do it. Yes?
When you introduce the variables, when you introduce the variables M, N, and H,
yes,
it assigns M to a natural, N to a natural, and H. It's because of the order. It's because of the length that you choose.
Look at the statement. The statement is that for all M and N natural numbers, blah blah blah. So if you say let's start picking M, it must be a natural number. I can call it T if you want.
Yeah.
Then
Okay. So
and everything. And I can be more precise and say let's introduce. Okay, this didn't work. Okay.
yeah, but I understand.
So he knows it because in the statement, the statement is about two natural numbers.
Yeah.
So he is able to guess the type of T.
So just to be precise, it's the order of the things, the order in which you introduce it matters. Because if I put H at the beginning,
yes,
H will be the natural number, right?
Yes, sure.
Okay.
It's the same order that you see. It's the same order written in the goal. The
Uh-huh.
goal is for all natural numbers M, N, this implies this.
Okay.
So, and you can really see happening. So you see, if you only introduce T, now the goal is that for all N, even N implies blah, blah, blah. So you can. And here now the same thing is just even N implies even T times N. But yes, the order matters, but it's the same order that you have in the statement.
Thank you.
Okay. So I know that what you can think at the beginning is that, yes, but if we just spent, I don't know, 10 minutes improving such a stupid thing, how is it possible to prove more interesting stuff? So there are two answers. First of all is that, of course, I'm not showing you the full power of the library, because otherwise it can do that. This proof, I mean, this theorem is already in the library, so you can just prove it saying someone else proved it. But also there is some sort of avalanche effect, meaning that at the learning curve is very steep at the beginning. We are very slow, having the impression that it's impossible to prove interesting stuff. But at some point, all we have done cumulates, and there is a real acceleration in the velocity of what we are proving stuff. But this happens after some time. So this is probably not going to happen during my course. But if you play with it, I can assure you that you can prove interesting stuff. Remember that the library knows essentially the mathematics as a first-year graduate student. So he knows quite a lot of mathematics. And we were able to prove a cutting-edge result in modern mathematics, something really done by a Fields medalist last year. So it's possible to prove with this level of details something really, really, really difficult. Okay, so, okay, no, this is not what I want to show you. This one, okay. So let's now the idea is that I'm just showing you several small proofs to show you several techniques we can use to improving stuff. And at some point you will also get used to the names of the theorem we are using that are not completely random. So now you are going to prove stuff about real numbers. Sorry, I really have to put it bigger, not bigger than this, because otherwise the statement is in 2 lines and it's essentially unreadable. So we want to prove this not so interesting theorem that if you have A, B, C, 3 natural numbers, A times B parentheses times C is equal to B times A times C. So if you don't put any parentheses, it associates multiplication and addition on the left. So you see that if you have a look at Lin's brain, the left-hand side has no parentheses. Even if here we put a parenthesis. This is because for him, multiplication and addition are associated to the left. If you forgot this, you can just you see if you go here with the mouse, you see that you can select A times B, but you cannot select B times C. You can select the product of the three, but you cannot select B times C because B times C doesn't exist on the left-hand side. So the left-hand side is really what is written here. On the right-hand side, you can select A times C because it in the Lin is showing a parenthesis. This is a computer scientist convention. Computer scientists hate parentheses essentially, so they try to avoid using parentheses all the time. And I admit that, I mean, at the beginning this was a little bit annoying for me as a mathematician, but now I get used to it, and I realize that even when I teach, I start don't writing the parentheses, and my students get crazy sometimes. But it takes some time to get used to it, but it's a good convention, I think. In any case, how can we prove this stuff? So, of course, we need to use some results about the real numbers because we don't want to. Lin, of course, has a definition of real numbers. He knows the definition of real numbers, and he knows some properties of the real numbers. For example, he knows that the multiplication is commutative. How it's called the theorem that says that multiplication is commutative? Well, with a lot of imagination, it's called mul-com. So you see that if you go with the mouse here, you see that what is mul-com? It says that with some crazy assumption, forget about it. Mul-com applied to AB is the fact that A times B is equal to B times A. Okay, so Lin knows that real numbers are a commutative semigroup. Whatever this means, it's not very important. But in any case, Lin knows that it can apply this theorem to real numbers. The interesting part of having this very general theorem is that maybe you want to apply multiplicativity of commutativity of multiplication to natural numbers. Also for natural numbers is true, and you don't want to write one theorem for natural numbers, one theorem for real numbers, one for rationals, blah blah blah. So we have the general one, and then we have theorems saying we can apply this theorem to real numbers and stuff like that. So essentially, mul-com AB is the statement that A times B is equal to B times A. And there is something interesting here. You see that here A and B are real numbers, but I never said take the theorem relative to real numbers. Lin just realized that since A and B are natural numbers, he must use the theorem relative to real numbers. Sorry. So it's not necessary to say to Lin, use specifically the theorem relatively to real numbers. Just say that A times B is equal to B times A. So now there is this keyword RW that is a shortcut for an abbreviation for rewrite. So what rewrite does is just rewrite the theorem in the goal. So mul-com AB says that A times B is equal to B times A. So if we rewrite this assumption in the goal, you see that in the goal we have A times B. So after this line, this A times B should become B times A. And this is what happens. I know it doesn't look very interesting, but still it worked. Now this is not finished yet, but because the left-hand side is associated to the left. So the left-hand side is B times A parentheses times C, that it must be equal to B times A times C. But this is exactly associativity of multiplication. So exactly as we had mal-com, we have mal-assoc. That is exactly the same statement, that A times B times C is equal to A times B times C, B times C. But of course, now we want to apply it to B, A, and C. So we rewrite mul-assoc B, A, C. And we see that, sorry, now Lin is happy. Okay.
So you were using two theorems there.
Yes, I used commutativity of multiplication and associativity of multiplication.
Oh, so in the picture that you put at the beginning, that will be 2 points. That
Yes,
a
yes,
third
exactly.
point
Yes,
as a
yes,
star.
yes, yes, yes.
Oh,
I mean, even much more than that, because you have to prove commutativity of multiplication, of course.
already if you do a picture of this theorem, you will have a lot of
There are the
points.
real numbers. This is a nightmare already.
Oh.
You see, I mean, real numbers are Cauchy's equivalence classes of Cauchy sequence of rationals. So it's proving that is commutative, whatever. It's a lot of work. I mean, even giving the definition of real numbers is a lot of work. Okay, let's try now to prove.
If you had 2 times A times B appearing, but you want to apply it the commutativity law only in one appearance.
Okay, this
you
was
do
my
it?
last example,
Oh,
but
sorry.
okay. No, it's a good question. So what he is asking now, if we want to rewrite, so we have an assumption saying that something is equal to something else. So we want to use this to rewrite something, but something appears twice in the goal, and we want only to rewrite once. There is a keyword to do that. So now this example, we have 3 natural numbers, A, B, C. We suppose that A plus C is equal to A plus B is equal to C. And we want to prove that A plus B times A plus B is equal to A times C plus B times C. Okay, so something that should be quite stupid. So, okay, the idea is that we need to, okay, you see, we want to rewrite H, but just once. Why not twice? Yes. So of course we want to rewrite H just here. So we want that this is good. We want, instead of having A plus B, we want to have C here. But we don't want to have C here. Otherwise we will get C times C equal to something. And so we say nth rewrite 1, that one is at the second place because these are computer scientists. So there is also nth rewrite 0. And you see that he just rewrote H only in the second appearances. In any case, all these little keywords that I'm using are called the tactics, and you can just go over with the mouse, and Lynn will show you a short explanation. So, for example, nth rewrite n rules performs only the nth possible rewrite using the rules. Blah blah blah. Okay. So rewrite is probably the most important tactic. It does something very, very easy, but still it's quite smart. Yes.
You are not introducing the variables here. Is it happening in the definition?
No,
example before we have to
see,
introduce them?
No, because in this example, you mean?
Yeah, we are not introducing them.
Because you see, okay, this is another way of, because the statement is not, this is something that mathematically is the same, but the statement is not for all A, B, C real numbers, then blah, blah. The statement is take 3 real numbers, then blah, blah, blah. I can write it equivalently like that. Oops, sorry.
And now we have
and
to.
now I have to start intros A, B, C.
Okay.
So the difference is that in the previous one, the statement was take 3 real numbers, then blah blah blah. Now the statement is for all 3 natural numbers, for all A, B, C real numbers, then blah blah blah. Of course, the two are completely equivalent, but there is a slight. I think that under the hood, for example, what the kernel received at the end, the two are exactly the same, but the way they are displayed is slightly different. But yeah, they are equivalent, and there is no difference essentially.
Okay.
So let's try to do another one just to show you what can we do. So now it's C times B times A equal to B times A times C. So I guess we have to switch the order of C and B. No, yeah, I can just start switching the order of B and C. Okay, it doesn't. It's not happy. C and B. Sorry, C and B. And now I can associate. Okay, I have to associate this. So what is the order now? Is BCA, BCA. And now I also have to switch the order of C and A. Oh. Okay. And you see, I mean, this is not fun. I agree. And we will see in 2 minutes that there are some shortcuts, but this is just to show you what we have to do. And you see that you can just write several rules in one line instead of introducing several lines. Okay, just something else I want to show you before moving to something more interesting is that sometimes there is. Now let's imagine that now I say to Lynn now to. So how can we prove this? So this is simply because. Okay, how can we prove it? Okay, this is interesting. So you remember that mul as such is the statement that A times B times C is equal to A times B times C. So you see that we cannot directly rewrite mul as such here. We want to rewrite mul as such in the other direction. So the key word is to use these little arrows like that. And I don't even have to specify the name of the variables. So Lynn knows that since I want to apply mul as such in the reverse direction, I'm probably applying it to A, B, and C. So the first time it can apply it is to A, B, and C. So it is able to guess the letters A, B, and C. And indeed, this is what it did. And now, how can I prove it? I can probably A, B. So now I want, I guess, no, this was a bad move, I think. Let me show how these stuff are really done. So I don't care about to finish this proof. Is one has just to find the right list of mul as such, mul comics, and so on. And this is not fun. I agree. Indeed, Lynn provides us with some automation to do something like that. We can just write ring. Nice. So what is ring? Ring is a tactic, is a powerful tactic. Is doing, you see, is doing something here. Here there is something to be proved. This proof is not difficult, but there is something has to be done. So the computer is doing something. I wouldn't say really smart, but it's doing something. So this is a stupid computation, but the computer is able to do it by itself. Okay, so when we write ring and we say that Lynn is happy, he says goal accomplished, we don't see any computation. But under the hood, the elaborator produced the proof. So I think that it's a good idea to show you at least once the real proof produced by a tactic. Okay, this is the very nice proof produced by ring. Oh. Yeah, exactly. Not very interesting, no. So this is what is. Okay, this is really awful. But so you see that we just write ring. The actual one is probably, I mean, I can prove it using mul as such and mul com twice or 3 times. But you see that this tactic ring is able to produce a very awful proof, but we don't care. We don't want to see it. So a ring essentially means do the stupid computation. This must be stupid, must be doable quite easily, and indeed Lynn does it. Here again, this is the same thing. So again, it's just a stupid computation. So if I say ring, it should work. Yes. You see them. So don't be too excited because I mean, here it's nice, but it's able really to only do stupid computation. So at some point, it doesn't work anymore. But we have several tactics for. So if you go here, you see that ring is a tactic for solving equation in the language of commutative semi-rings. We have a tactic for non-commutative rings that is called a non-commutative ring, unsurprisingly. So we decided to call it ring because this is much more used than the other one. If you want to do a computation with only so this is what it is a monoid. I don't know if we have a tactic for monoids. We surely have a tactic for groups, but you see the problem is that R with respect to the product is not a group. So I know that you can say yes, but I mean 0 is never a problem. Yes, but the computer is stupid. So okay, so just let's have a look of another example. So this is how to use hypothesis that we have. So now we have 6 real numbers. We suppose that A times B is equal to C times D. I mean some random stuff. And we want to prove that A times B times E is equal to C times D times F. Of course, here ring will not work because it's not using H and H prime. And this is true because of H and H prime. So you see that he says, I wasn't able to finish the proof. Try this other tactic, but it will not work either. So because the idea is really to use H prime. So we get rid of all the E. Now we use the associativity, and now we use H. But I mean, this is nothing interesting. It's really nothing smart. It's just to show you that how one can use local assumptions and so on. So let's do this one because we will have a new theorem. So now we assume that C is equal to B times A minus D, and that D is equal to A times B. And we need to prove that C is equal to 0. So why this is true? Because if we rewrite hype prime at hype, so we can do rewrite hype prime, sorry, at hype. And you see that now he rewrote hype prime. So he rewrote D equal to A times B, but at this assumption, not at the goal. If I don't write this, it says I don't know. I'm not able to rewrite hype prime because hype prime says D is equal to something, but there is no D in the goal. So I don't know what to do with this assumption, but I can say at hype. Now hype now hype becomes that C is equal to B times A minus A times B. Why this is 0? Because first of all, I can use mulcom. You see, there is no need to specify A and B. He understood it automatically. And now I have A times B minus A times B. This is, of course, 0. The theorem that says that something minus something 0 is called sub-self, as it's written here. So I can just rewrite sub-self. And it says, now hype is the statement that C is equal to 0. We want to prove that C is equal to 0. So how can we do it? I mean, how can we say, now we have it. We have the assumption. This is another tactic that it's called exact hype. So exact means, look, what we have to prove is exactly what we have. So this is done. Okay. Yeah.
Is that rewrite changing the value of hype? I mean, if I want to use it again later, but the original one, if I rewrote it, it's forgotten, or
so it's forgotten. If you want, you can you can either rewrite again in the reverse direction, but you can create a new assumption, and so you can duplicate assumption, of course. Yes, yes, exactly. Essentially, you can copy the value and okay. So no, let's just skip this one. So and yes, another thing I wanted to say. Now you see that here we use this theorem sub-self. Of course, so we used mul-com, mul as such, mul-add, I guess, somewhere. Now we have this sub-self. When this is going to stop? So the bad news is that essentially this is never going to stop. So that we have a huge list of stupid theorem like that is really, really, really huge. But pay attention to the fact that the names are really well chosen. So at the beginning, the name look like random, but they are not random at all. So now that I'm using this stuff since 2 years, I can usually guess the name without even having to look in the library. So I'm sure that I cannot forget that the theorem that A minus A is equal to 0, it's called sub-self, because the logic behind, we have a name convention that we try to follow quite strictly. So I'm sure that this sub-self is the name of this theorem. I'm sure that this theorem is in the library because it's so basic, and the name will be sub-self. For example, the fact that if you say A times